Last year in Humain, we actually did see SPADE, for those who were there. And this year, Adrien will present some progress in that area.
Thank you. So, hello, I'm Adrien Manuel Mascarenhas. I'm a French student in ELISA Aerospace, and I'm currently in internship in the Royal Observatory of Belgium. So today I'm here to present you the first meteor observation with SPADE. So what is SPADE? SPADE is a small phased area demonstrator. It's a radio telescope located in the Humain Radio Astronomy Station, which is 100 kilometers in the southeast of the Royal Observatory. And it's a system composed of 8 elements, organized like you can see here, with 1 element in the middle and the 7 other around. Each element is built of pair antennas oriented north, south, and east-west. This system works with software-defined radio technology that allows us to don't have mechanic technology in the orienting of the beam that we want. So we have 2 SDR in SPADE that allows us to get 8 channels for the 8 elements that we have. This SDR will catch the signals and transmit them to the processing computer. And SPADE is work on the beamforming techniques that will delay the signals to be summed, and it will be delayed relatively to the orientation of the signal that we want to take. And to sum the signal allows us to get a better and stronger signal in computing. So to observe meteors with SPADE, we use the forward scatter principle. This principle is to transmit a signal that will illuminate the sky, and this signal will be reflected on the meteors and will be catched by SPADE. So for this, we use as the beacon the BRAMS, the Belgian Radio Meteor Station transmitter that transmits around 50 megahertz, and we catch it with SPADE because SPADE frequency range goes from 20 to 80 megahertz, and the distance between them is around 50 kilometers, so that's enough to use a forward scatter. So for SPADE, the SDR that we use are the ITUS USRP X300. They are all built with 2 daughterboard twin RX that, as I said before, allows us to get a total of 8 channels. But we had to synchronize the sampling of the channels to get a good synchronization in sampling and to allow us to sum the signals. So for it, we decided to use the local oscillator of 1 channel to share it with a splitter to the other channel, and that allows us to get the same clock for each DEM without using an external clock. After it, we have to synchronize the phase of each signal to allow us to sum the phases and to make the calculation to get a proper beamform. So as I said before, the beamforming is based on delay. So the delay also changed the phases. So we have to have a good phase synchronization between each signals to allow us to get a better pattern, as we can see just here, that allows us to get a more stronger and a more directive pattern that could be with beamforming oriented in any direction. In that case, we had a 3 dB bandwidth of 10 degrees and a max gain of 21 dBi. That's much more than only one SPADE element, and that's much more directive also. So for the observation, as we use SDR, we control all the orientation and all the following that we want to do for the beam with a software. In our case, we use the software GNU Radio that allows us to get that kind of interface that we developed. That interface allows us to see all the different signals from each element, but also to control the orientation in azimuth, in elevation, and the gain that we want. And we also can see the computing that are already done with GNU Radio, but with a pretty bad resolution, and we cannot control really much that plot. So after we did really recently the first observation with SPADE for meteors, and we did that spectrograms that we developed. That's only FFT. There is no overlap for the moment. And we, for the moment, can see, for the first light, pretty good results. We can see a few overdense meteors, some underdense. Of course, we see the beacon at 49.97 megahertz, and of course we also see planes. But that's pretty good result for us, because for the first light we see already an epsilon meteor and a quite big overdense. So that's for us a pretty good result. And thank you for listening.
That's very well on time. Thank you. Questions? Adrien.
I have to ask you a question, right? What is the beam width that you use when you are making meteor observations then?
Antonio to the help.
No, the thing is that we just turned on the baby. Huh? These are the first images. If you read the date, can you go one before? This is last weekend. Huh? These are from the last weekend. So we only pointed to the zenith. But to the zenith, we have at 20 degrees.
Okay, so you see pretty much everything that passes in the band.
Indeed, but actually in the interface, well, I'm sorry, it's a little bit small, but here you have the controls to point the beam. So we actually, okay, let me say this quickly. This is live. When you open the application, this is live. You can see in real time the thing happening. So what I did, playing a little bit with my new baby, is that I turned the beam away from the beacon, and you can actually see the signal of the beacon diminishing. So the thing is working, but definitely, as Adrien just said, this is not processed. Huh? This is just raw data, no overlapping, no maquillage. It's just, that's why you can see the pixels. I mean, there's a lot of work to do. But well, we're very happy that it's on, huh? After all these years. We managed.
On the same token, maybe a bit of a personal remark. Maybe Hervé is thinking the same. The beam of 20 degrees is very narrow.
Yeah. It is, but it has also its benefits. Then you can see very faint stuff. That could be really interesting.
That's true. Yeah.
Yeah, actually, how many? 20?
Yes, it was, we see over 30 per hours. And the last weekend we observed during 23 hours, and we reached the 700 meteors detected. So that's pretty good result for the moment.
If
pretty much at. You should point somewhere in between Dourbes and Humain. You would maximize them.
And another one from my end, because I'm also very interested in the topic. if you have your counts by hour, you should see the daily pattern in the morning higher, in the afternoon lower.
Do not forget,
Still in time, eh?
do not forget this has been developed by the Solar Physics Department. This instrument is dedicated to observe the sun. So we, in this very moment, we can use it to play with meteors only when the sun is not around. Yeah, I mean, we could do it theoretically, we can do everything at the same time, but the amount of data that is producing is too much for the moment. You know, we are not saving each channel independently. We do the combination, and this is what we save in the end. So you have to choose the sun or meteors.
Winter is coming.
Yes, indeed.
Okay, thanks again, Adrien, Antonio.
There's an online question.
I don't see it. If you can repeat it.
So the question is, what is the maximum and minimum distance that can be received, can be between receiver? To be honest, I don't know the maximum and the minimum distance. If it's too small, we don't use forward scatter, but back scatter. But for the maximum, I don't know the maximum distance that we can have. Okay.
It is indeed.
As I've told that with BRAMS is currently 300 kilometers that we have.
And if you have the Graaf radar, you go to 1,000 kilometers, and you have already the curvature of the Earth that plays a role.